Now we're ready to tackle method 3, which I'll refer to as direct substitution. It's the final strategy, if you want to call it that you might choose to use when you're doing an integral. Some people will find this a bit easier than method 2, some won't. What I'm asking you to do is try them both, decide which one works better for you, and then stick with that method. You probably don't want to bounce back and forth between method 2 and method 3. Decide on which one you like best and then stick with it. Now the guess and check, any really simple problem you might feel that you can just do guess and check. So that's on the table for any simple one, but really once you decide between 2 and 3, stick with that choice and don't bounce back and forth between those two methods. One of the important things about looking at what we're doing now is remembering that you're going to eventually decide to use method 2 instead of method 3 or vice versa. So just keep that in mind. So let's go back to an integral we did earlier by method 2, which we refer to as substitution by matching. And let's do it a little differently. And this difference is going to be what we call method 3, direct substitution. So the integral that I want to tackle that we did earlier has an integrand of 4x times the quantity x squared plus 1 cubed. Now recall the steps for method 2 are listed here. We're going to modify them, and that modification will be method 3. The first 4 steps are the same. Let u be equal to the expression raised to the power. In this case, that'd be x squared plus 1. Compute du dx, the derivative of u with respect to x. That's 2x. Solve for du. That means you multiply both sides by dx and you get 2x dx. We did this exact same thing when we did this problem by matching. Step 3, though, is slightly different in this method. We solve for dx instead of du. That involves multiplying both sides by 1 over 2x, and you'll end up with dx equals 1 over 2x du. So step 3 is slightly changed. Step 4 says if the integrand has a numeric factor, move it outside the integral. Here there's a 4 that can be moved out, just as when we worked it by the other method. The last steps have to be wiped out and modified. Our new step 5 says to substitute the u just as before, but now you also substitute the expression represented by dx. So the x squared plus 1 is u, and we actually plug in 1 over 2x du in place of dx, and when we do that, we get an expression that can be simplified. Step 6 says to do that simplification. Notice that the 2 in the denominator can divide into the 4 and leave us with 2 on the outside. And the x in the numerator and the x in the denominator will just completely divide out. So when you take all of that into account, you get a 2 on the outside of the integrand, and all that's left on the inside is x cubed. So you get 2 times the integral of x cubed du. Simple enough. Now you carry out the integration using our formula for the general power rule for integration. We've used it several times now. Copy that 2 back down. It's just sitting there right now. It's outside the integrand, but don't forget to keep carrying it or your answer is going to be off by a factor of 2. But the general power rule for integration tells you that when you integrate u to a power, the result is going to have a 1 higher power. So the 3 becomes a 4. So you know that's going to be a u to the 4th. But it also has a factor of 1 over that new power. So you have to multiply out front by 1/4. But don't forget that 2 is still sitting there. And of course, every indefinite integral has a plus c. Simplifying, 2 times a 4th is a half. And the final step is to substitute the x values back in and then simplify it if you need to. Remembering that u is equal to x squared plus 1. We put that in place of u, and we have our final result. Method 3, direct substitution, starts off just like we're doing matching, but it diverts just a little bit and provides a method that some people like better than method 2. So as you practice these, decide which method is better for you and stick with it between method 2 and method 3. Remembering that you always go back to the guess and check for the simpler problems if you want to. And as a final thing to point out, I will say that this is exactly the same answer we got when we did this same problem using substitution by matching. Either method works. It's just a matter of personal preference. 6 examples follow this discussion, modeled on this direct substitution method, and they're step by step. So what I'd like for you to do is solve each one of these integrals when you see them on the screen, but pause, solve the integral yourself, and then compare that to what you see. You can restart the video, and if you got it right, you can look through and make sure that step by step it matches up to what you did. If you made a mistake or you got stuck, you can use that step-by-step process to see where you got stuck, and you can do that 6 times. And the key here is practice. I want you to take this very, very seriously. If you want to learn the basics well, now is the time to do it. Please, please set aside some time where you can practice undisturbed, taking it very seriously, taking it one step at a time, and not just watching it worked out on screen. You're never going to really learn it if you don't struggle through it yourself. It should be an interactive process. So please take this seriously and do the legwork. Suppose we wanted to evaluate this integral, and suppose we wanted to do it by our method of direct substitution. First of all, you're going to have to go through these steps, which can look quite daunting, but as you practice more and more, the steps will start to flow better from one to the other, and it'll become second nature to you, but it does require lots of practice. Before we actually get started with this, let's copy the problem back down again. Now let's just go through the steps. Step 1 says to set u equal to the expression raised to the power. Here that would obviously be the x minus 6. So we set u equal to x minus 6. Step 2 says to compute du dx. That's the derivative of u with respect to x. That would just be 1. Step 3 says solve for x. So we're going to multiply both sides by dx. On the left, the dx is divide out, and you're left with du equal dx. Technically, we're solving for dx, so if you want to, you can write that dx equals du. Step 4 says if the integrand has a numeric constant factor, move it outside the integral. That's a number that's being multiplied by everything in the integrand. There's not one of those here, so that doesn't even apply. Step 5 says to substitute both the u and the expression represented by dx into the integrand. And notice that this step will remove every trace of the x and the dx, for that matter, from the integrand, if you've done it properly. So we go back here and we look at this. We know that u is equal to x minus 6, so we actually go in and physically remove the x minus 6 and replace it with u. And we do the same. Dx is equal to du, so we replace the dx with the du. Notice that when we're done, we have no x's or dx's, we have only u's and du's. Step 6 says to simplify the integrand, but that's about as simple as you'll ever see an integrand, so there's really not anything to do here. Step 7 says to use the general power rule for integration. The general power rule, remember, says that you can integrate u to a power by increasing the power by 1, going from n to n plus 1. And here, you'd be adding 1 to 3 halves, and just remember, I don't want to spend much time doing arithmetic, but adding 1 to a fraction, in particular 3 halves, is like adding 2 halves to 3 halves, that gives you 5 halves. So the new power will be u to the 5 halves, and then you have to multiply by the reciprocal. 1 over something is the reciprocal of it. The reciprocal of 5 halves is 2/5. And as always, with an indefinite integral, you have to add plus c. Step 8 says to substitute the x values back in and simplify the result if necessary. Here, the x minus 6 was what u was. We put the u in there. It was not there in the beginning, so getting rid of it, the x minus 6 goes back in instead of the u. And let's just write it at the top. And keep in mind, if you have any doubt that you got the answer right, all you have to do is take the derivative of what I've just boxed in there and convince yourself when you take its derivative, you get what you started with. You can always check these integrals by differentiating and see if you get what you started with. So if you end up with that answer, differentiate it and see if you get back the integrand that you started with. If you do, you know you got your integral right. In any case, there's your answer. Suppose we wanted to evaluate this integral. And suppose we wanted to do it by our method of direct substitution. First of all, you're going to have to go through these steps, which can look quite daunting, but as you practice more and more, the steps will start to flow better from one to the other, and it'll become second nature to you, but it does require lots of practice. Before we actually get started with this, let's copy the problem back down again. Beginning with step 1, set u equal to the expression raised to the power. That's obviously the x minus 6. So we set u equal to x minus 6. Step 2 says to compute du dx. That's the derivative of u with respect to x, and that would be 1. Step 3 says to solve for dx. So we want to multiply both sides by dx to clear the fractions. That means the dx is on the left, divide out, and you get du equals dx. Technically, we're solving for dx, so some people would be more comfortable writing the dx first, so you could write that dx equal du if you like. Step 4 says if the integrand has a numeric, which is just a number, a constant, factor means something multiplied through, move it to the outside of the integral. And here you see that there is a 2, a factor of 2. The 2 is being multiplied by everything else in the integrand, so move it outside the integral. Step 5 says to substitute both the u and that expression represented by dx into the integrand. The idea is to remove every trace of x and dx, for that matter, from the integrand. So if we take the x minus 6 out and put u in its place, remembering to copy that 2 down, do not forget that 2 is still in front of the integral sign. We get u to the 3 halves power instead of x minus 6 to the 3 halves power. And then since dx is equal to du, if we take the dx out and replace it with a du, we get this integrand, the integral of u to the 3 halves du. Now we're ready to simplify, but that's about as simple as an integral as you could ever have, so there's really nothing to do as far as simplification. Now we're going to apply the general power rule for integration. And again, I can't say this enough, keep carrying that 2 along. If you get caught up in your process and forget to carry that factor along, you're going to be off in your final answer. So it's 2 times what we get when we integrate u to the 3 halves power using the general power rule. The general power rule basically says when you're raising u to a power and integrating that, you increase the power by 1. So we have to add 1 to 3 halves. I don't want to make a big deal about working with fractions, but remember 1 is 2 halves, so if you add 3 halves and 2 halves, you get 5 halves. But you also have to multiply by 1 over that new power. 1 over something is just the reciprocal of it, so if we've got 5 halves as the new power, the reciprocal will be 1 over 5 halves, which is just flipping the fraction upside down, is 2/5. And of course, every indefinite integral has to have a plus c on the end. Step 8 says to substitute the x values back in and simplify as you need to as you're working through this. As you can see, 2 times 2/5 is 4/5, and if you plug the x minus 6 back in to get rid of the u, you get the quantity x minus 6 raised to the 5 halves power, and then you have the plus c. Remember, we put the u in order to solve the problem. That was not in the original problem, so it has to come back out at the end. And keep in mind, if you have any doubt that you got the answer right, all you have to do is take the derivative of what I've just boxed in there and convince yourself when you take its derivative, you get what you started with. You can always check these integrals by differentiating and see if you get what you started with. So if you end up with that answer, differentiate it and see if you get back the integral that you started with. If you do, you know you got your integral right. In any case, there's your answer. Suppose we wanted to evaluate this integral, and suppose we wanted to do it by our method of direct substitution. First of all, you're going to have to go through these steps, which can look quite daunting, but as you practice more and more, the steps will start to flow better from one to the other, and it'll become second nature to you, but it does require lots of practice. Before we actually get started with this, let's copy the problem back down again. Step 1 says to set u equal to the expression raised to the power. Here, that would obviously be x squared plus 3, so we set u equal to x squared plus 3. Step 2 says to compute du dx. That's the derivative of u with respect to x, which is 2x. Step 3 says to solve for dx. We can get rid of that fraction by multiplying both sides by dx. The dx is on the left, divide out, leaving you with du equal 2x dx. But remember, we're solving for dx, so we need to multiply both sides by 1 over 2x, so that the 2x's on the left divide out, leaving you with just dx. So now we know that dx is the fraction 1 over 2x multiplied by du. Step 4 says if the integrand has a numeric, which is just a constant, a number, a numerical factor, move it outside the integral. There is an 8, which is a factor of the entire integrand, so we want to move it out. Step 5, which is really the heart of the process, says to substitute both the u and the expression represented by dx into the integrand. So since we know that x squared plus 3 is equal to u, we can take that x squared plus 3 out and put it in u. And I also want to emphasize that that 8 still has to be written down as you go down. You're not doing anything with it, but it does carry down the process. So now I want to do the substitution. The x squared plus 3 is equal to u, so I put in u instead of that. And then, since dx is 1 over x times du, I put that in place of dx. All my substitutions are done. Now I want to simplify the integrand, and the first thing I notice is that the x's divide out. At this point, you should be rid of every trace of x and dx in the problem, and here you can see now that those x's divided out that that's in fact true. You can also notice that the 1/2 multiplied by the du is just a constant factor, so you can bring it out front with the 8, and that leaves you with a very simple integral to evaluate. We do have one more simplification step, but 8 times 1/2 is 4. Now we can focus on the integral itself. The integral of u to the third du can be handled by the general power rule for integration, which is what step 7 asks you to use. That tells you that the integral of u to a power is obtained by raising the power by 1 and then multiplying by 1 over that new power. So since the power in our problem is 3, we want to add 1 to 3 to get 4. And then we want to multiply by 1 over 4, which is 1/4. You've got a little simplification here, of course. 4 times 1/4 is just 1. And also, you always have to add a plus c on an indefinite integral. So doing both of those things, 4 times 1/4 being 1, and adding your plus c, you end up with u to the 4th plus c. Final step, step 8, substitute the x values back in, simplifying if needed. So the u goes out, because we put the u in ourselves. It was not in the original problem. Now, after we're done with our integration, we take the u back out and put back in the x squared plus 3, and we're done. And keep in mind, if you have any doubt that you got the answer right, all you have to do is take the derivative of what I've just boxed in there and convince yourself when you take its derivative, you get what you started with. You can always check these integrals by differentiating and see if you get what you started with. So if you end up with that answer, differentiate it and see if you get back the integrand that you started with. If you do, you know you got your integral right. In any case, there's your answer. Suppose we wanted to evaluate this integral, and suppose we wanted to do it by our method of direct substitution. First of all, you're going to have to go through these steps, which can look quite daunting, but as you practice more and more, the steps will start to flow better from one to the other, and it'll become second nature to you, but it does require lots of practice. Before we actually get started with this, let's copy the problem back down again. Step 1 says to set u equal to the expression raised to the power. As we've discussed, if there's ever any doubt about what u should be, at least in the context of the problems that we're dealing with now, you should choose the power of x that's higher. So in the numerator, you've got a 4th degree expression, and in the denominator, you've got that x to the 5th plus 1, which is a higher power. So that's your best choice for u. Just a rule of thumb, but it's going to get us through this until you get better at understanding what's going on. Right now, we're just trying to get off to a good start. So we choose u to be x to the 5th plus 1. Step 2 says to compute du dx. That's the derivative of u with respect to x. So that would be 5x to the 4th. Step 3 says to solve for dx. So I'm going to multiply both sides by dx. On the left, the dx is divided out, and I find out that du is 5x to the 4th dx. But remember, we're solving for dx. So I need to multiply both sides by 1 over 5x to the 4th, so that the 5x to the 4th divide out, leaving me with just dx. Remember, I'm trying to solve for dx. Well, if I do that, I've also got to put a 1 over 5x to the 4th on the other side of the equation. And when all is said and done, I know that dx is equal to the fraction 1 over 5x to the 4th multiplied by du. Step 4 says if the integrand has a numeric that is a constant factor, move it outside the integral. And here you see that there is a factor of 3 that you can move outside of the integral sign. Step 5 says substitute both the u and the expression represented by dx into the integrand. Just a simple substitution. Remember though, you've also got to carry that 3 along. It's not doing anything right now, but you have to carry it along because it will multiply through in the end. So we're physically taking out the x to the 5th plus 1 and putting u in its place. And for dx, we're removing it and putting in what it's equal to, which is the fraction 1 over 5x to the 4th multiplied by du. Now we want to simplify the integrand. The first thing I hope that you notice is that there's an x to the 4th in the numerator and an x to the 4th in the denominator, which will divide out. You also notice that there's a 1/5 left as a factor inside the integral, which can also be moved out, and it'll eventually multiply by the 3. All that leaves inside the integral is a 1 in the numerator, a u to the 3rd in the denominator, and the du on the end. Look at that very carefully because this is important. You can also clean it up a little bit by noticing that 3 times 1/5 is 3/5, and that 1 over u to the 3rd is u to the minus 3. And the reason I want to write it that way is because I'm looking ahead. I know I'm going to use the general power rule for integration, and it tells me how to integrate u to a power. So that's why I want it written that way. Speaking of that, the 3/5 is just going to follow along for the ride, but we need to use the general power rule for integration to evaluate that integral. The general power rule for integration tells you to integrate u to a power, you add 1 to the power. Adding 1 to a negative, be very careful. Minus 3 plus 1 becomes minus 2, so it becomes u to the minus 2. But then you've also got to multiply by 1 over that new power. So 1 over minus 2. In other words, a negative 1/2. And as always, with any indefinite integral, you have to add a plus c. We can clean up some of the arithmetic, multiplying those two fractions, top times top, bottom times bottom. A positive times a negative will end up being a negative value, so it's going to be negative 3/10 times that u to the minus 2 plus c. And at the end, you're just going to substitute the x values back in because we put the u in. The u was not in the original problem. U is equal to x to the 5th plus 1. So we put the x to the 5th plus 1 back in place of u, and we're done. And keep in mind, if you have any doubt that you got the answer right, all you have to do is take the derivative of what I've just boxed in there and convince yourself when you take its derivative, you get what you started with. You can always check these integrals by differentiating and see if you get what you started with. So if you end up with that answer, differentiate it and see if you get back the integrand that you started with. If you do, you know you got your integral right. Suppose we wanted to evaluate this integral, and suppose we wanted to do it by our method of direct substitution. First of all, you're going to have to go through these steps, which can look quite daunting, but as you practice more and more, the steps will start to flow better from one to the other, and it'll become second nature to you, but it does require lots of practice. Before we actually get started with this, let's copy the problem back down again. Step 1 says to set u equal to the expression raised to the power. And as we've discussed, when there's any doubt in your mind about what to choose for u, a good rule of thumb for these type of problems is to choose the expression with the higher power of x. So there's only an x to the first power in the numerator, there's an x to the second power in the denominator, so that would be your natural choice for u. So we choose u to be x squared minus 6x plus 1. Step 2 says to compute du dx. That's the derivative of u with respect to x. That would be 2x minus 6. Then solve for dx. I would multiply both sides by dx. Notice on the left the dx is divided out, and you get du is the quantity 2x minus 6 times dx. Generally speaking, when you have a common factor in your differential, chances are you're going to need to factor out that common factor. Not always going to work that way, but most of the time it will. So I'm going to factor a 2 out of that and rewrite the differential du as 2 times the quantity x minus 3 times dx. And I can see that it was a good choice already because when I look back at the original integrand, there is an x minus 3 there. That makes me feel good about my choice of factoring that out. In any case, we're solving for dx, not du, so I need to multiply both sides by 1 over the quantity 2 times x minus 3, so that the 2 times the x minus 3's will divide out on the right, leaving me with dx being 1 divided by the quantity 2 times x minus 3, all multiplied by du. So I've solved for dx. Step 4 we don't need. There's nothing to factor out. There's no common factor that's a constant. Step 5 says to substitute both the u and the expression represented by dx into the integrand. So it's just a straightforward process. We let u be x squared minus 6x plus 1, so you simply put that u under the square root in place of the x squared minus 6x plus 1. Also, the differential's got to go. The dx we found by our calculation to be 1 over the quantity 2 times x minus 3 times du, so that comes out as du, and now it needs to be simplified. Notice that the x minus 3 in the numerator divides out with the x minus 3 in the denominator, and that's going to happen if you've done this correctly. Your x's and dx's have to come out of there. So when you simplify it, you also notice that there's a 1/2 factor that's shown up, and we can take that 1/2 and move it outside the integral. Remember, we can always take a factor that's a constant and move it outside of the integral sign if we like. So cleaning it up a little bit, the 1/2 comes out, the square root of u is in the denominator still, everything else is gone except for the du. Now we go back to our little knowledge of square roots. We know we're going to have to get powers into this problem because our general power rule for integration tells us how to do it with u to a power. So we want to get rid of the square root. So we change it to 1/2 power. Not only that, we don't want it in the denominator. We want to think of that 1 over u to the 1/2 as u to the minus 1/2. We're thinking ahead and we're trying to match this to the general power rule for integration. And now it's time to use it. The general power rule for integration tells us how to take the integral of u to a power. That's why we wanted to change the square root of u to the 1/2, and why we wanted to change 1 over u to the 1/2 to u to the minus 1/2 so that it would fit this power rule for integration. So now we're ready to use it, and it's going to require us to increase the power of u by 1. So we're going to take the minus 1/2 and add 1 to it. Well, minus 1/2 plus 1 is like minus 1/2 plus 2/2. That leaves us a positive 1/2. So when we add 1 to minus 1/2, that becomes a power of 1/2. But remember that 1/2 sitting out front has to be used as well. So I'm just going to copy it down and then do what I just said. Add 1 to the minus 1/2 to get a positive 1/2. And finally, the general power rule for integration says that we have to multiply by 1 over the new power. 1 over a number is just the reciprocal of the number, so 1 over 1/2 is 2. So we have to put a 2. And as always, with indefinite integrals, we have to put a plus c. Now we're sort of playing cleanup. 1/2 times 2 is just 1, so we end up with u to the 1/2 plus c. And the very last step says to substitute the x values back in, simplifying if needed. Remember, we put the u's in ourselves. They weren't in the original problem, so now they have to go. The u comes out, and the expression that it was equal to, which is the x squared minus 6x plus 1, goes in its place to give us our final result. And keep in mind, if you have any doubt that you got the answer right, all you have to do is take the derivative of what I've just boxed in there and convince yourself when you take its derivative, you get what you started with. You can always check these integrals by differentiating and see if you get what you started with. So if you end up with that answer, differentiate it and see if you get back the integrand that you started with. If you do, you know you got your integral right. In any case, there's your answer. Suppose we wanted to evaluate this integral. And suppose we wanted to do it by our method of direct substitution. First of all, you're going to have to go through these steps, which can look quite daunting, but as you practice more and more, the steps will start to flow better from one to the other, and it'll become second nature to you, but it does require lots of practice. Before we actually get started with this, let's copy the problem back down again. Step 1 is to set u equal to the expression raised to the power. So here we want to let u be equal to the expression 2x cubed plus 4x. And as I've said, if you're debating about what u should be, it's probably going to be the expression with the highest power of x. You've got this expression to the third power, which I chose. The alternative would be the 3x squared plus 2 with the power of 2. And since 3 is one higher than 2, you probably want to choose u to be the 2x cubed plus 4x. Step 2 says to compute du dx. That's the derivative of u with respect to x. That would be 6x squared plus 4. Step 3 is to solve for dx. So I will multiply both sides by dx. The dx is on the left, divide out. And that leaves you with du is equal to the expression 6x squared plus 4 times dx. Now remember, we're solving for dx, not du, so I need to divide both sides by that 6x squared plus 4, or equivalently multiply both sides by 1 over 6x squared plus 4. In either case, you'll notice that the 6x squared plus 4 divides out on the right, leaving just dx. So now we know that dx is the fraction 1 over the quantity 6x squared plus 4 multiplied by du. I also mentioned before that most of the time, if there's a common factor in the differential, you're probably going to want to factor it out. And I noticed that in that denominator, 6x squared plus 4, there's a common factor of 2. So I factor a 2 out of that. The denominator becomes 2 times the quantity 3x squared plus 2. I feel good about that choice when I look back in the integrand. Beside the factor beside the dx is in fact 3x squared plus 2. So that makes me feel that I made the right decision to factor out that 2. Most of the time you'll find that to be the case. Step 4 says if the integrand has a numeric, which is just a constant factor, you can move it outside the integral. That really doesn't apply here. You don't need to do that at all here. Step 5 says to substitute both the u and the expression represented by the dx into the integrand. So I'm going to take that u and put it in place of 2x cubed plus 4x. And if you'll notice, what that does is it turns it into u cubed. I'm not doing anything to the 3x squared plus 2, but I also want to replace the dx, and I notice that dx is that fraction 1 over the quantity 2 times 3x squared plus 2 du, so I plug that in place of dx, and when I do that, something nice happens that'll allow us to do step 6, which is to simplify the integrand. And what happened nice about this is that there is a 3x squared plus 2 that divides out of that integrand. And at this point, what you've done is remove all the x's from the integrand, which is what you want to do. Continuing to simplify it, you'll notice there's a 1/2 factor that can be moved out front. The 3x squared plus 2 is divided out, so all that's left is that 1/2 that you factored outside the integrand, the u to the third power, and all that's left to the right is that du. So what you've done in this simplification step is get rid of all the x's and dx's and leave the integrand with only u's and du's. Now that allows you, because by now you've gotten rid of all the x's, there are no x's, there are no dx's, that allows you to go to the general power rule and integrate it because we've got the integral of u to the power. Also say at this point, don't forget the 1/2 that's out front. It's just sitting there right now, but it is still there, so go ahead and write that down, and then apply the general power rule for integration. The general power rule for integration says if we want to integrate u to a power, we integrate by increasing the power of u by 1, so that u to the third becomes u to the fourth, but we also multiply by 1 over that new power. So we do multiply by 1 over 4. And of course, every indefinite integral has a plus c. We can sort of wrap up the simplification now by multiplying 1/2 times a fourth and getting an 1/8. And now we're ready to do step 8, which is to substitute the x values back in. Remember that we put the u's in there. They weren't in there originally. So in the end, we have to put the x values back in. So I take that value, 2x cubed plus 4x, and put it back in place of the u. And that gives us the final answer. And keep in mind, if you have any doubt that you got the answer right, all you have to do is take the derivative of what I've just boxed in there and convince yourself when you take its derivative, you get what you started with. You can always check these integrals by differentiating and see if you get what you started with. So if you end up with that answer, differentiate it and see if you get back the integrand that you started with. If you do, you know you got your integral right. In any case, there's your answer.